This is Mike. He's a senior leader at your company who has heard many data science buzzwords, but has very little knowledge of statistics and mathematics. On the other side, he's making a ton of money. Mike wants you to build a classification model that will be very easy to understand and easy to interpret. So you quickly decide to build a decision tree, since a tree is very easy to interpret. This is how a tree looks like, obviously, but we will flip our tree upside down to show the model and its components. In this episode, we will learn how to flip trees. Yes, you've heard it, trees, not houses, simple trees. And to be more specific, a Gini classification tree.
Okay, I want to show you something really funny today, but it's going to have to be our secret. Don't tell Carolina I did this because I'm going to get into trouble, all right? We're going to take her plant that she loves so much, this one here. We're going to take this plant and I'm going to teach you how to build a machine learning model. So come with me. Now just imagine it's a tree. Carolina calls it a tree. So what we do in machine learning is we flip the tree. And this is the base of our tree with the main split variables, our branches, and terminal leaves. And that's exactly how we build a decision tree.
What I am drawing here is a tree that we will be able to build and analyze by the end of this episode. To better understand how to build it, we should first talk about its elements. A decision tree will have a main split variable at the top of the tree, in the trunk of the flipped tree. The main split variable will have the most splitting power. In our case, it's age, and it has the most splitting power. And the most optimal splitting value is 25 years old. For example, if the observation has less than 25 years, it goes left because it was labeled with the yes answer. On the other side, if the observation has more than 25 years, it goes to the right, following the no path. Now let's go left, where observations have less than 25 years. In that tree branch, our split variable is mass. If mass is less than 31, the observation goes left. If mass is more than 31, the observation goes right. Now let's assume that our observation has less than 31 mass. It will go left and hit a terminal leaf. A terminal leaf is the end point of our tree where the observation gets classified. In our case, the terminal leaf is labeled as 0, which means business failure. However, in our training dataset, this terminal leaf had 181 failures and 172 successes, which makes it a 51% probable business failure. Our tree has many terminal leaves, and our observations can fall into any of these leaves depending on how they flow through the branches. This is a sample dataset with diabetes statuses for Pima Indians. In this dataset, we have 3 features: pregnant, pressure, and age. Our labels are POS for positive diabetes test results and NEG for negative diabetes test results. We will use this sample dataset to understand how to build a decision tree using the Gini index. The first question we need to answer is, which feature will be selected first? In other words, which variable will be at the top of our flipped tree? To answer that question, we'll need to calculate the Gini index using the formula at the bottom of the screen. And the variable that has the lowest Gini will be selected. We will make the following assumptions. 1. The best value to split pregnant is 5.5. 2. The best value to split pressure is 72. And the best value to split age is 31.5. We will first analyze the pregnant variable. And let's take a look at a frequency table. We can see that we have split pregnant by 5.5, And what this table shows us is how many positive and negative people, Indians, did we have that had less than 5.5 pregnant. We see 3 people that are positive and 4 people that are negatively labeled with pregnant less than 5.5, a total of 7 people. Now let's take a look at people that were pregnant higher than 5.5. We have 3 positive and 1 negative, which totals 4. Now using this frequency table, we can calculate the Gini index. Gini for pregnant less than 5.5 is going to be equal to 1 minus 3 divided by 7 to the power of 2. 3 because we have 3 positive people, and 7 because we have 7 total people in this class, in this label. Now, minus 4 divided by 7 to the power of 2 because we have 4 negative people and 7 total people in that category. And that Gini index is equal to 0.489796. On the other hand, the Gini for pregnant above 5.5 is equal to 1 minus 3 over 4 squared. 3 because, again, we had 3 positive people that have pregnant higher than 5.5. And then minus 1 divided by 4 to the power of 2 because we had 1 negative person that was pregnant above 5.5. So that Gini index for pregnant above 5.5 was equal to 0.375. Now, if we put those two numbers together, the Gini for pregnant below 5.5 and Gini for pregnant above 5.5, and calculate a weighted average, we will get the last line, which is 7 divided by 11. That's the weight that the pregnant below 5.5 has. As you can see, we have 7 that are below 5.5, but we have a total of 11 people, 7 plus 4. Okay, so our weight is 7 divided by 11 times the Gini for pregnant less than 5.5, which is 0.489796, plus 4 divided by 11, because we have 4 people that are pregnant higher than 5.5, and 11 people in total, times 0.375, which was our Gini index for pregnant above 5.5. Now, this weighted average is equal to 0.448052. And this 0.448052 is the entire Gini index for the pregnant variable, assuming this split value. Our second variable is pressure. We split pressure into 2 groups, lower than 72 and greater or equal than 72. For the group that is lower to 72, the count of positive people is 4. And the count of negative people is 3. Again, total of 7 people with pressure less than 72. For the group with pressure higher or equal than 72, we have 2 that are positive, 2 that are negative, and a total of 4 people. Altogether, again, 11 people. Same 11 people. The Gini index for pressure less than 72 is equal to 1 minus 4 over 7 squared. 4 because we have 4 people that were positive, minus 3 over 7 squared. 3 because we have 3 people that are negative in the pressure less than 72 group. The total Gini score for pressure less than 72 is equal to 0.489796. Now let's take a look at the Gini for pressure greater or equal to 72. That is equal to 1 minus 2 over 4 squared, 2 because we have 2 people that are positive in that group, minus 2 over 4 squared because we have, again, 2 people that are negative in that group. And the entire Gini index is equal to 0.5. For the combined weighted average Gini index for pressure, we have 7 divided by 11. We have 7 people that have pressure less than 72, and 11 people in totals, times 0.489796, plus the other group, 4 divided by 11, because we have 4 people with pressure greater or equal to 72, times 0.5, because that's the index for Gini pressure greater than 72. And the overall index is 0.493565. Last but not least, the age variable. And if we take a look at our frequency table, we will see that age was split into two groups, below 31.5 years and above or equal 31.5 years. In the group with younger observations, below 31.5 years, we have one positive member and 5 negative members, a total of 6 members. In the older group, above or equal to 31.5 years, we have 5 positive members and 0 negative members, a total of 5 members. So the Gini index for those that are younger, below 31.5 years, that is equal to 1 minus 1 over 6 squared, 1 because we have 1 positive and 6 because we have 6 total, minus 5 divided by 6, 5 because we have 5 negative young observations, and that is squared. So that equals to 0.28. On the other side, the Gini index for people that are older, above or equal 31.5 years old, that Gini index is equal to 1 minus 5 divided by 5 squared, 5 because we have 5 positive observations, minus 0 squared, 0 because we have 0 negative observations. And if we do the math, that Gini index will be equal to 0. Last but not least, the entire Gini index for age is equal to 6 divided by 11 because we have 6 younger people and 11 total, multiplied by 0.28 because that's the Gini index for the younger people, plus 5 divided by 11, 5 because we have 5 older people, times 0 because the Gini index for the older people is equal to 0. Now, if we add that weighted average, we will get a total Gini index for age equal 0.151515. Now that we have calculated all the Gini indexes for all the 3 variables, let's select the best feature for the main split variable at the top of our flipped tree. The lowest Gini index will win. So for the 3 variables, the Gini comparison looks as follows. For pregnant, it's 0.44, for pressure it's 0.49, and for age it's 0.15. Age was the smallest, so age wins. Age will be put at the top of our flipped tree. Let's draw our flipped tree. At the very top, we'll have age, with the split value being 31.5. If we go to the right, then it means that the observations are older than 31.5. If we go to the left, that means that yes, age is less than 31.5, which means we have younger observations. On the right-hand side, where the answer was no, meaning the observations were older than 31.5, all the observations are positive diabetes. On the left-hand side, where the answer was yes, meaning the observations are younger than 31.5, we have another smaller data set, a subset from our original data set. Let's consider the new data frame with remaining observations. We will repeat the same process one more time. We will build our tree even further by selecting the next best split variable. For the new smaller dataset, we'll need new assumptions. The first one is that the best value to split pregnant is 3.5, the best value to split pressure is 51, and the best value to split age is 29.5. First feature, pregnant, and let's take a look at the frequency table once again. Now the pregnant is split at 3.5, so we have 2 groups below 3.5 with 1 positive and 2 negative observations, total of 3, and above or equal to 3.5 with 0 positive and 3 negative observations, total of 3. Together, 3 plus 3, 6 observations in this small data set. Now let's take a look at our Gini indexes. The Gini index for pregnant less than 3.5 is equal to 0.44, and the Gini for pregnant greater or equal 3.5 is equal to 0. So the overall Gini for pregnant, using the weighted average, which means 3 divided by 6 times 0.44 plus 3 divided by 6 times 0, is equal to 0.22. So the new Gini index for pregnant is 0.22. Our next variable is pressure. And again, let's take a look at our frequency table. We are splitting pressure at 51. So in the first group, below 51, we have one positive and one negative observation, total of 2. And in the group above or equal 51 pressure, we have 0 positive and 4 negative, total of 4 observations. So the Gini for pressure below 51 is equal to 0.5, and the Gini for pressure above or equal 51 is equal to 0. Now the overall Gini for pressure, and again it's the weighted average, is equal to 0.16666. That comes from 2 divided by 6 times 0.5 plus 4 divided by 6 times 0, 0.1666. Last but not least, the age frequency. Age was split at 29.5, so the first group is below 29.5, with one positive and two negative observations, a total of 3 observations. The second group in our frequency table is age above or greater or equal to 29.5, with 0 positive and 3 negative observations, total of 3. So the Gini index for age below 29.5 is equal to 0.44444, and the Gini of age greater or equal to 29.5 is equal to 0. So the overall Gini for age is equal to 3 divided by 6 times 0.4444 plus 3 divided by 6 times 0, which is equal to 0.2222. What we can do now is select the best feature for the second branch in our flipped tree. And again, the lowest Gini index will win. So the comparison is as follows. For pregnant, the Gini index is 0.22222. For pressure, it's 0.166666. And for age, it's 0.2222, which means that pressure wins. It had the lowest Gini index. Back to our tree. We will start with the age variable, less than 31.5. We've calculated this before. If we go right, this means a no answer, which means that no, the age is not less than 31.5, it's greater than. If we go left, that means yes, the age is lower than 31.5, which means younger people. If we go right, all are positive diabetes. If we go left, we had selected pressure to be the next winning variable, and we said less than 51. We go left for yes, we go no for right. So if the pressure is above 51, which means no, we go to the right, all are negative diabetes. But if the pressure is less than 51, which means yes, we go to the left, and there is one positive and one negative observation in that group. Let's call it a success. We know how to calculate a tree, how to build it, how to select split variables. Decision trees are easy to calculate, easy to understand, and easy to present. Back to our studio. Let's try to code our decision tree with the Pima Indian dataset. And we'll try to build a simple one for the first 11 observations and see if RStudio gives us the same split values for our three features. And let's see if we can build this very same tree that we have designed in our video. Okay, what I'm going to do is I'm going to start with installing 3 different packages. So install dot packages parentheses and double quotes. I'm going to install the MLBench library. The MLBench library has a lot of data sets for machine learning, classification data sets, including the Pima Indian dataset. So if I click command return, it's going to install my MLBench package. In my case, it had to restart the R session, and now it's pulling data from the CRAN. I'm getting our beautiful warning message saying that the downloaded binary packages are in this folder. Okay, the next library that I have to install is called rpart. rpart will have all the functions that we need to build our tree, to train our tree. The third package I'm going to install is called rpart.plot. Parentheses, double quotes, rpart.plot. This package, and click command return control enter, and this package has functions that we will use to plot, to draw our decision tree. And now that I have installed all these packages, I will call them using the library function. Library mlbench, library rpart, and the library rpart.plot. Okay, these three libraries command return all three lines so that my packages are loaded into my session. What I want to do next is take a look at my data set. So in the script, I will say data and parentheses Pima Indian diabetes. Pima Indian diabetes. The first one. Okay. So now if I click command return, it will save a data frame in my environment right over here, in this environment right over here. Okay. It's going to save the Pima Indian diabetes data frame with 768 observations and 9 variables. So if I expand this, I'm going to get all my variables. Okay. Now in our decision tree from the video, we have used only 3 of these: pregnant, pressure, and age. So let's do that. Let's subset this one for those 3 variables only. I'm going to call my new data frame my_df, and in my script write my_df. Reverse arrow, I'm going to take the Pima Indian diabetes data set and select the first variable, the third variable, and the first variable, comma, the third variable, and the 8th variable, and the 9th variable with our labels. Okay, so now if I run this, my DF is exactly the same 3 features and 1 variable with labels that we've used previously in this video. But in the video, we have subset the observations to the first 11 so that we were working on a smaller data set. So let's do that. My_df2, reverse arrow, will take my df and take the first 11 observations only. So 1 through 11, comma, and all the columns, all the 4 columns variables. Okay, so if we run this, we will have a smaller data frame, my df2, with 11 observations, exactly the same 11 observations from our example from this video, and 4 variables, 3 features and 1 label. So let's take a look at it. We have our pregnant, pressure, and age, and diabetes. As you can see in our environment, the diabetes is a factor. So right here in our environment. So to make our lives easier, we will convert diabetes from a factor to a character. All right, so let's go back to our script. And here I'm going to say my_df2 $diabetes, reverse arrow, as dot character, and then my_df2 $diabetes. Okay. Command return, control enter. Going back to my environment, I see diabetes, character, POS, NEG, POS, NEG. So positive, negative, positive, negative. I have characters now. So I can use the G_sub function. G_sub function. Let's do that then. I will say that I want to convert the positive to 1 and negative to 0. Okay. So my_df2 $diabetes. I'm going to use the G_sub function and replace the NEG with a 0 and my_df2 $diabetes. Okay. Beautiful. Okay. So let's go back to our environment, and we can see that we have still a character with POS for positive and 0. All the negatives, NEG, were replaced with a 0. Okay. So we have to do the same for the positive, convert the POS to a 1. So let's write a similar line of code in our script. my_df2 $diabetes, reverse arrow, G_sub, parentheses, double quotes, POS, comma 1, and comma my_df2 $diabetes. Okay, and now if we go to our environment, which is right here, we will see a variable that is still a character. We're going to convert it in a moment, but has 1 and 0. So the positive was converted to a 1, and the negative was converted to a 0. So let's go back to our script. In our script, we're going to have to still convert this from a character to numeric. So my_df2 $diabetes, reverse arrow, as dot numeric, my_df2 $diabetes. Okay, so let's submit this. Beautiful.
back to our environment, which is right here. We see diabetes that is numeric, 10101011. It's numeric. Good, exactly what we need. All right, so now to build our tree, what we will do is we will say our part. Okay, that's the function to build our tree. It's called the same way as the library, our part. And here we're going to insert our function formula in R. So the independent variables are pregnant, pressure, and age, and the dependent is diabetes. Okay, so dependent diabetes, and now our squiggle is going to be pregnant plus pressure plus age. That's how we denote this model. Diabetes will be a function of pregnant, pressure, and age, plus age. And the data is equal to my underscore df2. Now we have to specify the method. Method equals, we want a classification decision tree. Okay. So this is what I have in our rpart function. Rpart, diabetes is a function of pregnant and pressure and age. That's how I read this, right? And then data equals my df2, method equals class. I will save this in a object. I'm going to call it my underscore tree, reverse arrow, and then use the rpart function. Okay. Beautiful. We just trained our tree. Okay, and if we go to our environment, we will quickly see my underscore tree with a lot of things that we don't know what they mean, right? It's just black magic. It's a list of 12 elements with a data frame, with leaves, with weights, with complexity, scores, etc., etc. Doesn't really matter. Okay, but what matters is if we can plot this tree. So I'm going to use now the rpart.plot function, rpart.plot function to plot my underscore tree, and the type will be equals to 2, and extra will be equals to 2. Those are just two parameters that we can specify to make our tree more beautiful. Type equals 2, extra equals 2. Okay. But the most important thing here is to specify the name of our tree, my underscore tree, that we have defined 2 lines above. Okay, so let's plot this. Command return, control enter, and it gives us a beautiful tree of only one node. Okay, so why is this happening? Well, it is happening because, see, a tree of one node in our plot section. This is happening because we have such a small data set. Okay, such a small data set, the tree, the algorithm doesn't know how to split. We knew how to split, right, by the Gini index, but the computer is saying it doesn't make any sense, right? Since the computer doesn't know how to grow this tree, it's basically clueless because the data set is so small, 11 observations only, and 3 features only. As you can see, this one here is extremely small, right? It's only one node. What we can do is add a few controls, a few parameters to tell our computer, tell the algorithm how to design the tree, how deep to go, how deep to look for the Gini index, right? So after the method equals class, I'm going to do a comma, and in any line of code, I'm going to say control equals to. See, a list of options that control details of the rpart algorithm. Okay, so control equals to, and I'm going to say rpart.control. Okay, that's my function. rpart.control is my function, and here I'm going to define a few very key elements to tell our algorithm how big the tree should be. The first one is min split. Min split will be equal to 1. So what is the minimum? What is the minimum size that our split should be? Okay, and we'll keep it to the minimum, to the bare minimum. Okay, minimum is 1. Right. Now the second argument here will be min bucket. What's the minimum size of our bucket of data? 1. Okay, 1 observation. Again, we are dealing with 11 observations, so we have to keep everything to a minimum. Okay. And last but not least, something called a CP parameter. This stands for complexity parameter. Okay, this is used to prune or grow our tree. If you want to grow our tree, we set this complexity parameter to a lower value. Let's say 0.001. I'm making it super small so that the tree can grow. Okay, small CP, bigger tree. Bigger CP, smaller tree. We prune it, okay? Okay, good. So now with these extra 3 parameters, these 3 extra options, we will again recalibrate our tree, retrain our tree, and plot it. Ah, beautiful, beautiful. So let's take a look at this tree, because it looks extremely similar to the tree that we have designed in our video, right? We have age as the main split variable, age. However, the split value is not the same. It's not the same. It's ballpark similar, but it's not the same, right? And then if we go to the left, the answer is yes, which means age is less than 32. And on the contrary, if you go right, the answer is no. So age is not less than 32, which means it's higher, older people. So older people go here, and they get classified as positive diabetes. See this one, right? Positive diabetes. But if it's a younger person, so yes, age is less than 32, we go left. We go left. And the general classification here is a negative diabetes. Good, okay. Now the next question is pressure. Same thing what we had using our Gini index and our assumed split values. Good, okay, so next one is pressure. So if pressure is greater or equal to 58, if the answer is yes, go left. And these were classified as negative diabetes, okay? But if the pressure is not greater or equal to 58, meaning it's lower than that, we go to the right. And now the algorithm said there is one more split variable, right? And it's pregnant. Let's use that information to split our data, right? Because we still had 2 observations in this bucket. So let's split them. So this being said, we also have one more split value, pregnant greater or equal 7. So if that's true, if the answer is yes, pregnant is greater or equal 7, we go to the left, classified as negative diabetes. If the answer is no, meaning pregnant is less than 7, we go to the right, and it's classified as positive diabetes right here, this green terminal leaf. Okay, so we actually were able to replicate the same tree that we've calculated previously, and using our assumptions to the split values, Okay, so now, since we can replicate what we have calculated, almost replicated the same thing, age having the highest splitting power at the very top of our tree, pressure being the second split variable. We did not look at pregnant, but apparently, since we have specified so minimal options in our R-part function, it was able to include pregnant as a next split variable in a new branch. Okay, good. So now we have replicated it for our small data set, the 11 first observations. What if we were to do a similar tree for all the data set? I'm gonna scroll up in my code. Okay, so now what I'll do is I'll go back to the code and remove this subsetting for the first 11 observations. I want all the observations, okay? So I'm simply going to say that my underscore df2, reverse arrow, my underscore df, in line number 11. Okay, so I want all of my observations. So same 3 features and my labels, so age, pressure, pregnant, and my diabetes levels. And then I want all the observations, all 768 observations. Okay, so let's run all of this code and take a look at the tree. Now look what's happening. If you actually look pretty close, our tree is now enormous. It's so big that we can't really see anything. We have thousands of terminal leaves and hundreds of split variables, okay, of branches, right? We have hundreds of branches and thousands of terminal leaves. Why is this the case? Well, as you guys remember, what we have mentioned before is we need to specify some controls in our R-part function so that the small data set, that the tree for the small data set is more accurate, is deeper, looks for the Gini indexes at a deeper level, right? Here, that's not necessary. So we will need to adjust these controls so that our tree looks a little bit more reasonable, is a little bit smaller. So let's do the min split at 20. Let's do the min bucket at 15. And the CP will do at 0.05. Let's refit this tree and let's plot it. oh, now we have pruned it too much. Now we don't see anything because there's only one node, right? I've increased the CP value to 0.5 and we can't really see anything. So let's decrease the CP value to 0. Let's say 1. Refit and rpart.plot. Aha. And this tree seems to be more reasonable, right? This size, this complexity of this tree seems to be a lot more reasonable than the first one that we couldn't read because we had thousands of terminal leaves. And it's also much bigger than the one node tree we just saw 2 seconds ago, right? So much better than this, right? My computer's getting a little bit slow. This is much, much better. So what we have here is we are splitting by age twice. Then we're splitting by pregnant. Then again, we're splitting by age. Then by pregnant, and then again by age. So we are not using pressure anymore. Really interesting. So when we included all of the other observations, and now we have 768 observations, we don't need to use pressure anymore, okay? Apparently the Gini index for pressure was too high, and it never got to be included in our tree. Okay. So this being said, what I want us to do now, we've increased the size of observations, but now let's allow the algorithm to include all of the different features in our data set. So what I am going to do is I am going to remove this. Okay, I'm going to remove this subsetting on variables in our data set in line number 10. Okay, and I will also add a few variables here to the rpart function. What variables can I add? Well, I can add variables such as triceps, maybe mass, maybe pedigree. Let's do that. So age plus triceps plus mass plus pedigree. Okay, good. And now I'm going to run the code from scratch, from the beginning, from line number 8, where we see data, PIMA, Indian state diabetes. I'm going to run all this code to re-import our data set with all the different variables. All right. And I'm going to refit the tree and plot it. Beautiful. Okay. So let's take a look at this tree. I'm going to zoom in just a little bit. Let's take a look at this tree. Okay. The font is a little bit small, but I'm going to explain. Our main split variable is age. Not surprisingly, we've seen age so many times. Our manual calculation gave us age as well with the lowest Gini index. Then we have mass. Oh, so maybe mass has a huge impact on diabetes, right? Okay. And then we have, what else do we have? We have mass. Oh, pedigree is pretty high in our tree.